First, I would like to thank the organizers for giving me this wonderful opportunity for presenting my talk and organizing such a wonderful workshop. As introduced, I'm going to talk about generalized detectors at colliders and how we can probe confinement, which we care about in this conference, obviously, through hadronization dynamics. So to set the stage, let me begin with the question, what confinement dynamics is high energy scattering, like this process depicted here at colliders, actually sensitive to? Of course, my title already gave it away, but let me introduce a little more. So if you actually look at high energy scattering that involves hard scattering process, then you actually have these kind of partons that are produced at short distance associated with this hard scale order Q. So as some order 1/Q. This then receives some perturbative radiative corrections and undergoes collinear and soft splittings, which you can, again, perturbatively compute. But at some point in the dynamics at long distance associated with this gap scale, 1/λ QCD, these splittings or partons undergo confinement. And there are many different Monte Carlo models that are in the market that try to model these kind of hadronization process. Here you're actually seeing a PITIA, which actually use something called Lundstrom model that literally creates linear potential between these quark pairs or color partners, which obviously is motivated by things like flux tubes that are discussed in this conference. Then there is some kind of rules on how this string breaks into forming bounded hadrons that you actually see in the experiments. And with something like this, you can actually compare with the actual experimental calculations. So in some sense, from collider physics point of view, for especially in QCD, the broad goals can be summarized as the following, where you actually have this kind of bounded hadrons that you see that are sensitive to all these non-perturbative process, whereas there is something that you can actually perturbatively compute using perturbative QCD. And so the goal is, what are observables that gives us perturbative control on such collider process that involves so much non-perturbative dynamics? And this goes by what's called IRC safe or infrared and collinear safe observables. And can we actually learn something about the underlying non-perturbative dynamics in a systematic and controlled fashion, right? And what actually experimentalists do to study these kind of process is actually observe these asymptotic hadrons in their detectors that are collected, right? They're not actually sensitive to or going in there to see the underlying pertonic process, but what they observe is these bounded hadrons. So what experimentalists are doing can be kind of summarized as studying the correlations of these asymptotic detectors. So to achieve our goals or to answer these questions, you need to better understand these detectors, right? And this has been a very interesting subject of study to not just in the context of these confining theories like QCD, but in conformal field theories as well. And there are formal ways of understanding the space of detectors that live on these asymptotic null infinity. And I won't go into it too much, but there are a lot of work like this where you literally have hammer, just as in this perturbative QCD case, and you have some detectors that are asymptotically located, where you try to also understand, just like you understand the local operator and its expansion, you try to understand the detector and its expansion. And there's been a lot of works in CFTs, and some people are in the audience as well. And the natural question for me, who's interested in QCD, is what about for confining theories, right? Can confinement dynamics actually be probed using such asymptotic detectors and its correlations? So this is the outline of the rest of my talk. So first, I will introduce what generalized detectors are interesting from collider point of view. And then I'll introduce what's called detector functions, which are basically Wilson coefficient between the UV and IR detectors in confining theories. And then talk about operator product expansion of these generalized detectors. And if time permits, I have a lot of slides, then I will briefly flash some applications in actual applications in collider setting. So let me begin by introducing generalized detectors. Probably the simplest and most important detector is, as you're familiar, is called ANIC operator or energy flow operator, which is nothing but actually detecting the flow of energies that are given by some solid angle directions. And there has been many formal and phenomenological studies of these ANIC operators, which I'm not going to summarize. But one thing that's crucial in this talk is that energy flow operator forms a very natural object under which you can organize infrared and collinear safe observables. And this you can kind of intuitively understand from this simple language that hadronic detectors and partonic detectors in terms of energy, because energy is conserved, are identical, right? When I actually go into studying the correlations of these ANIC operators, say 2-point correlation as a function of the angle, you do actually see some confinement effects set in. So here, again, it's given by the angle between the two detectors, where left is very collinear and this is back-to-back regions. First, when you actually have a uniform isotropic radiations like this one, you actually get completely uniform flat distributions. This kind of situation can occur in a strong coupling regime in n = 4 or heavy state or large charge as the source. I believe Gabrielle is going to talk about the next correction to this uniform situation for large charge case for energy correlators. Now, if you actually go to weakly coupled case, instead of something like this isotropic radiation, you form a jet-like state, which then undergoes these kind of collinear splittings in the language of QCD or light ray OPE that gives you this scaling relations. But in the case of confining theories like QCD, instead of it infinitely radiating more and more radiations, at some point it confines where when the angular scale becomes small enough to give you this kind of a rapid fragmentation regions where things are again uncorrelated free streaming hadrons. And this you can actually even see in real data. This plot is actually identical to this plot, just there's some Jacobian. And you can see the theory calculation in the OPE regions, which is completely perturbative, agrees beautifully with data. And then the data at some point confines into this hadronic regions. So it is kind of true that ANIC operator, by going sufficiently to small angle, you can actually see confinement set in, but this is totally non-perturbative regime where the momentum exchange is non-perturbative. And my question is then, can we actually do even more, right? And that's what motivates these kind of generalized detectors. So again, from the detector point of view, the fact that ANIC operator is less sensitive to hadronic effect or confinement dynamics is again intuitively understood from the fact that the energy is conserved. So if I actually have a parton like this gluon come in, and then if the universe is somehow magically formed out of type A hadron and type B hadron, just for simplicities, if I measure all hadron energies, then these two energies are conserved, and therefore you're not sensitive to this confinement magic that happens in between. But this is related to, again, the question that generalized detector is related to the question, the fact that in actual experiments, you can do a lot more than just measure energy. You can measure the charge of the hadrons or flavor of the hadrons or different quantum numbers of the hadrons. So if you now measure, instead of all hadron energy, you measure the energy of the hadron type A or hadron type B, you are no longer, your energy is no longer identical to energy of the parton you begin with. So you're sensitive to this confinement magic, right? Or you can even do inclusively over all hadron flavors, but you can weight this energy by higher powers or lower powers, which would not, again, be identical to the parton energy that you started with, right? So you actually can be sensitive to this confinement magic. So the generalized detectors that we are trying to study is of this type, where you can actually put arbitrary energy weighting or put different quantum number to have exclusive measurements on different hadrons and study their correlation functions. And there are lots of data, especially at LHC using jets, where you can actually have unique opportunity to study these detectors and its correlation functions. So I want to answer the question, how do we actually renormalize these generalized detectors from confining theories like QCD? And what is the OPE limit of these generalized detectors? Right? So detector functions are what's needed to actually bridge the connection between what's really observed in terms of hadrons into what's calculable in partonic detector language, right? So this is kind of more of a philosophy where these massless UV detectors actually live on null infinity, whereas gap particles are following time-like trajectories. So there is actually a matching that's necessary between the IR detectors and the UV detectors. And the detector functions are basically the Wilson coefficient that gives you a connection or matching between these two type of detectors. And in QCD, to be explicit, you can have UV detectors of twist 2 type that are formed in terms of these local operators of local twist 2 operators. And then you can light transform to then get these light ray OP or detectors of these partons. And then hadronic detectors then must be matched between this UV detectors and then the IR detectors. And again, for the ANAC operator, this detector function is just unity. Yes?
Here that you're not.
Sorry, I couldn't hear.
Take color for that. You have more match.
Absolutely, absolutely. Yes. So you can actually have a situation where, because UV detectors are not sensitive to distance where the distance is order lambda QCD. So then you can have a case where IR detectors that are very short distance that can match onto UV. But I would say you can then just write down, it's still following in this form, right? It's just you have a more, or yeah, pick. Yeah, but we definitely, those cases are considered as well. So the detector functions are, as you may guess, non-perturbative functions that describes how partonic degrees of freedom turns into hadronic degrees of freedom. And if it's familiar to you, it's related to something called fragmentation functions or track functions. So these are non-perturbative functions that describe how momentum of the initial parton converts into hadrons with some particular quantum number. In this case, where we took the case of charged particles. So this is an example of a detector function that gives you a distribution. And you can see that it's peaked around 2/3. So you can kind of understand this intuitively as if all hadrons in the universe are made out of pions and roughly 2/3 of them are charged. So you can see the initial momentum of the partons, if I only measure charged hadron, will be roughly 2/3. These are some the UV and IR poles of these detector functions that are necessary to cancel the IR divergences in the calculations and describes the perturbative evolution as well, but let me not get into that. But once you have such detector functions, then you can actually match your IR detector, in this case, say for charge, you measure only the energy of the charged hadrons in terms of these UV detectors, which are given by, or the matching coefficient is related to the first moment of these detector functions. And once you have matched them, you can also consider the OPE of these two IR detectors, which then gives you higher sensitivity to higher moments of these track functions and higher spin states of the light ray operators. You can do something even more sophisticated if you want to study generalized correlations in terms of ones involving different quantum numbers, different energy weighting of these types. Then you need multi-dimensional detector functions. Here's one example where you actually measure both the momentum distribution of minus charge hadron or plus charge hadron. And this is, for instance, necessary to study correlation of energy plus energy minus correlation functions. And then you can match them and then also consider OPE in terms of these detector functions as well. So let me briefly give you a summary of these from the operator product expansion language. So again, you have two IR detectors, which can be matched in terms of UV detectors, and they're all OPE coefficient is given by the usual UV OPE coefficients times some moments of these detector functions. And I do not have the time to describe, but there are actually power correction terms that are sensitive to soft hadron effects that are actually suppressed by lambda QC over hard scale Q that are also given by these kind of detector matching language. And this is from the OPE language, but you can actually do what's called the QCD factorization that actually allows you to go even beyond leading logs. And we have many of these calculations that are now at next leading log or next leading log order that also agrees with the OPE language that I discussed. But yeah, if you're curious about these formulas, then I can explain more after the talk. So let me now go to the applications once these detectors are sort of matched and now we have the framework. What are actually some interesting detectors and correlation function to study these confinement magics? And there's already quite a bit of work on this. So we are currently working on these higher weighted energy detectors. And there's also, which is sensitive to these non-perturbative power correction effects, as I will show. And then there are charge detectors, which are advantageous for these experimental measurements to carry out precision measurements. So this is very good for precision calculations. There are more exclusive charge detectors where you are, instead of measuring all charge, you measure, say, unlike sign charge pairs, or you measure flavor information. And these are actually sensitive to discriminating different hadronization mechanisms, as I'll show. You can also measure different heavy states energy correlators, which are sensitive to mass effects that I will show. And you can even measure spin correlations on top of the energies, which you can do as I will show, something like Bell inequality tests using these detector language. So again, I'll very briefly show it, but you can see if I measure E-square correlations, there are actual experimental data. When you compare with the energy correlation with single energy weighting and energy correlation of higher energy weighting, namely 2, their scaling is completely modified by integer amount. And this is actually giving sensitivity to these power correction terms that actually have different angular scaling, right? So here, this blue is what you might expect from the naive OPE that goes as 1 over theta square or 1 over z in the other variables. But you can actually see that there are non-perturbative power corrections that actually change the scaling by an integer amount that you actually see in these higher energies weighting things. This has many other applications, but let me not go into that. You can also measure energy correlators on these charged hadrons only. This is advantageous from the experimental point of view because if you measure all particle versus tracks have much more accurate experimental measurements because of these tracking systems. This allows you to do precision measurements of fundamental constants like Strong-Kropping constant. And there are some works that we are doing. One can also measure more differential charge information. Say you measure unlike charge pair correlations. This is interesting from the confinement point of view because if you look at this kind of a string breaking model of confinement, you can imagine if the string has a conserved electromagnetic charge, then if you have a plus charge hadron, then you would likely to see minus charge hadron nearby. And indeed, as you see here, the plus minus or unlike sign correlation is enhanced relative to like sign correlation, which is a signature of sensitivity to these kind of hadron breaking effects. I won't go into it too much, but you can do even more differential or exclusive things where you actually tag even the flavor information, say pi minus and k plus, which is preferred by these long-string model type hadronization. And you can see that long-string type hadronization model given by this red and blue of this type correlations has a very different behavior compared to the clustering model correlation. And actually precisely in this region in gray, which is sensitive to these confinement transition. So you can actually visibly distinguish between two different confining models by this observable. Here we are also looking at heavy correlations where you have two heavy hadrons. When you actually compare with the inclusive case, as I was saying, this confinement transition is totally non-perturbative. You cannot compute it perturbatively. So if I compare with perturbative calculation, this just kind of goes up and never gets this confinement transition. Now, if you actually do heavy states, these are perturbatively computable because heavy quarks are in the perturbative scale, and you can actually see this kind of a bound state forming or the mass effects set in these kind of correlations. And you are also now, because only measuring heavy states, you are effectively picking out this glue to QQ bar splitting states. And once you actually pick out these glue to QQ bar splitting states, you're actually able to also look at how these splitting, in particular splitting, is modified in the medium dynamics, for example. So instead of, as I was saying, it's interesting to ask the question of how is this correlations modified if I actually prepare them in different backgrounds. And one of the interesting questions from the experiments is to study these correlation in quark-gluon plasma, and by effectively tagging or isolating this glue to CC bar type splittings by measuring only heavy hadron states, you are able to see how this correlation is modified for this particular splitting in the medium versus vacuum. Finally, you can even measure spin correlations, and that can then source how these hadron pair states are, whether they are in entangled state or separable state or CSSH violating states. And this will then give you actual information on whether your underlying hadronization that gave rise to these bound states are actually quantum or classical. And this is just the beginning. There are many general correlations and detectors that one can study. And by asking the right question, I believe one can actually probe confinement at these colliders observables. So let us explore different landscape of well-defined detectors and its correlations. Thank you.
Question about that. And then when it comes to generalized, you go through all of that on data.
Yes, absolutely. I mean, so this is data, which is E-squared detectors. There are tracked measurements of these correlations in lab data that have been reanalyzed. There has been also measurement of this plus minus correlations on both LHC and RIC. And this correlation has not been measured, but there's been a lot of interest to measure this as well. And then heavy correlations has also been measured at LHC as well, which actually you can see these kind of a mass peak. Yeah, and this one is more complicated because it involves like 2 lambdas, but it's something that one can calculate, measure like at colliders like EIC, which has a lot of luminosity.
Questions?
Do you have any idea how this picture will get large and that is, you don't expect to see many patterns, right? Because producing every pattern you pay one away and will do some simplification.
Yeah, I mean, maybe one thing I would say is that there's been a lot of calculations on these things and comparisons to n=4 super Yang-Mills calculations and certain planar limits and how those are related to analytic forms of QCD. In terms of, yeah,
There you don't have hadronization. Right?
there you don't have hadronization, sure, but that's more on the perturbative side, right? But in terms of, yeah, non-perturbative, I don't know if I can say anything beyond that. Yeah.
All right, there are no more questions. We're gonna have a